Sure is. Thank you for telling us. So let's say we have a simple expression for velocity, like 5t squared. No, let's not use 5. Let's make it easy. Let's make it 6t squared minus 3. That's good. That's it. We'll just do that. This is our velocity. When I was talking to you about taking this and figuring out position, I told you about taking the antiderivative to do so. That's skipping actually quite a few steps. And it's skipping the nomenclature on the way this is supposed to look. So today, let's not skip through that so that we can see why the integral symbol and all of that is used the way it is. Because velocity is actually dx dt. And although we talked a little bit about this in mechanics a couple weeks ago, the idea of splitting the derivative, that's what we actually do when we go to take an integral, is we do split the derivative. Whether that's because it's a differential equation or not, we are going to be preparing to take an integral by splitting the derivative. So when I replace velocity with dx dt, I now have a derivative. And this is technically a differential equation. It's just not a very interesting one. But to figure out what x is, the first thing I do is split the derivative. I will multiply both sides by dt. Now, although this technically should be considered a number, it really isn't. Not in a specific sense. We treat it kind of like a number or like a variable. We treat it like it's actually, delta t. But it really isn't, because it's supposed to be so infinitesimally small, it is to approach the limit of delta t going to 0. So we treat it a little differently than an actual number, but we do in algebra kind of use it like a number to shift it around, which is why we can put it on both sides of the equation now, and why we're able to multiply both sides by dt to split the derivative into two pieces. Now, the next step we would do is we would technically say that we want to take the integral of both sides, which requires that I draw the function for the integral, which is a script s, actually. It's supposed to be an s, or it's supposed to at least look like an s, because this symbol and this symbol technically mean the same thing. They both are a summation symbol. Now, with calculus, we have found that summation can be done using the integral function, meaning finding the antiderivative and setting limits. That's an integral function. So when we take the integral of both sides, we are technically going to be finding the antiderivative of both sides. Now, there are several steps to do this, and the first is to recognize that this represents the original function. And although we don't ignore the d, we focus on this. This is telling us which variable is the one to pay attention to. It's the variable of integration. So this technically is the integrand. I think that's what they call it. And this is our differential variable. But when we look at this and we say it, we're going to be saying, I'm going to take the integral of 6t squared minus 3 with respect to t. That's what we would say if we wanted to say what this is telling us to do. Just like on the left side of that equation, we are also saying that we are going to take the integral of the function of 1 with respect to dx. There's an implied 1 here. Now, in this class, one of the things that we will need to do is recognize that our integrals usually have predisposed limits, meaning we tend to know what the limits are that we're integrating. Even if they're not specific numbers, we know what it is we are looking for in our integral. Meaning we tend to know that time starts at 0 and goes to some time in the future. These are called the limits of the integral. And the limits are physical constraints or boundary conditions that we impose on the integral. There's two different kinds of integral. There's definite and indefinite. Definite integrals come with limits, boundary conditions. Indefinite integrals don't. The only difference is that an indefinite integral won't have limits placed on it, won't have numbers here and here. What you have to do will still be the same in both cases. But if you have an indefinite integral, because there's no limits, you have to add the constant at the end. We did that when we took the antiderivative. We talked about the fact that if we took the limit here, our constant would be the starting position. But in calculus, you're just going to put a c there. And generally, you'll try and figure out what c might represent with some boundary conditions given later. For us, we are often going to have boundary conditions that are themselves variables. So it would not be uncommon for us to have a boundary condition that says go from T1 to T2. So our boundary conditions will not often be numbers, but other variables. What you do with those is the same. And let's talk about what we do now. What we do next is we take the antiderivative of whatever is in here. You are going to be building a huge toolbox of antiderivative topics in calculus. Things that work for trig functions, things that work for logarithmic functions and exponentials, things that work for odd fractions or mixed kind of fractions. You will be building an entire toolbox of every single different kind of function that there is. In fact, I don't have it anymore, my table. At one time, before internet, believe it or not, we had to look things up in books. We have the internet now, so we don't do that. But there was and I don't know where it went. I'm afraid somebody stole it from me because I had like the 48th edition of this book. And it was a new edition every year. And it was just a set of mathematical tables. For example, it was every single trig identity there was, every one of them. It had every single integral that could be done, every one of them, and had just pages and pages of integral tables. Every different kind of formulation of a function existed in this book. And I wish I knew what happened to it because I used to love to just take it out there and put it out there because it reminded us of the old days. But let me tell you, having that book made you a pretty popular person when you were in like physics and engineering classes because there was no internet. And if somebody gave us an integral that we couldn't do, you just pulled the book out and you looked it up. Now, you're going to learn a bunch of these things, but trust me, you're going to forget all of them about 2 years after calculus, maybe not even that long. So having access to stuff like on the internet, I use Wolfram Alpha now for all my integral needs. What do you guys use? Yeah, it hasn't come up yet. So trust me, even my old calculus textbook had 300 different integrals in the margins and in the tabs of the book. So trust me when I say these are simple. There are lots that are impossible. And that's why you look them up in a book. Anyways, long story longer, this part, you have a process for finding the antiderivative of a polynomial. So that's what you do next. And in this case, my polynomial antiderivative is going to be 2t cubed minus 3t. So I found the antiderivative of my function. But that's just the function on the right. There's a function on the left I also have to find the antiderivative of. And in this case, because it's just a 1, my antiderivative of 1 is just x. Or the left side, I'm taking the antiderivative with respect to x. And the right side, I'm taking the antiderivative with respect to t. I have to pay very close attention to what variable I'm working with on either side. Calculus does almost everything with y and x We are all over the place in here. So pay attention to the variable that you're integrating with. So next, I think in calculus, they want you to put a bracket over there. I was taught to just put a line like that, but I'm gonna be like Mr. Bright and Mr. Bashir, and I'll put the bracket because I think they. What's that? Oh, good. They're back to the line because that's what I did for 30 years. You just put the line over there. It doesn't matter. What you're supposed to do is you're supposed to lay out what your limits are here. A reminder that you still have to apply the limits. I didn't put limits on the left side. I should have, but it doesn't really matter that much. Now, the limits tell us that we have boundary conditions that have to be met, but all you have to do when it comes to dealing with the limits, move everything, is you put this in for the function first. So 2t2 cubed minus 3t2. And then you subtract, putting this limit in. 2t to the 1 cubed minus 3t to the 1. And you're done. You have effectively taken the integral and applied your limits. If, however, this was an indefinite integral and did not come with limits, like so, and there were no limits, all I would do after I was done doing my antiderivative was add a constant. Calculus will make you put a C. We would never put a C unless we, had no idea what that constant was. For us, we will have an idea of what that constant is, and every single time we do one of these problems, we will always know what it means because we are trying to deal with something that's in the physical world. Math is just trying to have fun with numbers. And I'm not making fun of math, but yeah, that's all they do is making fun of, that's all they do, fun with numbers. So that's the process of taking an integral. That's what the symbology means. So when we have a function that's specifically an integral, like the work function, the work function is a specific integral. It's a little more complicated than our standard integral, though, because the work function has integration built into it, but it also has a dot product built into it because our values here are vectors. And because they're vectors, it makes it a little bit more challenging for us because we have to take into account how the force and the displacement are angled relative to my integration. And that adds a layer of difficulty here. Max will like this conversation because this specifically is a line integral. And he's been very fascinated with them over the last couple of days. I don't really know why, but I'm excited because he's excited about it. Hold on, I need coffee, not tea.
I have coffee today, just so you know.
I'm impressed, Joey.
It's like 2-day-old coffee that I got on my way to our meeting on Monday, but like still good.
All right, so I was about to have a little bit more respect for Joey, and I just want you all to know that if he had just stopped when he said I was having coffee, we would have been fine. But instead, he had to go the extra mile there and say 2-day-old coffee, but it's still good.
Well, okay, they made it too sweet, right? So I brewed coffee at home and then just like diluted the too sweet coffee that I had left over with the like new coffee. So it's not all old.
So is this getting better or worse for all of us? For me, I can appreciate that because Well, how should I say this? I don't like my coffee that sweet either. But I probably would have just tossed the coffee and not saved it. Because it looks like a Dunkin' cup.
It's Starbucks.
Is that a Starbucks cup?
Yeah, with like the new
Okay.
fancy sippy lid too. You don't want to see that lid. It's kind of gross because it's 2 days old.
Yeah, I was going to do something, but I decided no. 2-day-old coffee in a Starbucks cup. Well, okay. Well, this has been fun. The reason I'm frustrated is because when I started the lady in the tube doing our recording here, I forgot to spotlight my video. So now when I download this video, I will be unable to put it on YouTube because the moment Joey started talking in the video, it's going to switch to his face and we'll get him in the video. Now his face will be in the video. Not that I don't mind that his face is in the video, but I'm not allowed to post anything that has student faces in it.
For
Now,
the record, I consent.
oh,
The
and now it's
record
on video,
There
so
we go.
I could post it. Joey will now be not internet famous on my YouTube channel, but he'll be on the YouTube channel, so I'll post it.
Blow this up, guys.
Have you guys, I mean, I'm gonna get pause here for this, just a second. I don't care if this goes on, but how many of you have watched any of the videos that have like my little head in the corner? Because I did it for mechanic. Are they lame? I mean, my videos are lame anyways. I know they're lame. Is it worse with the head in the corner? I am really into it. Well, the reason I bring it up is because, you know, as I do the, I don't want to post videos. It's believe it or not, it's a lot of extra work, Alex. But I do it because like kids are absent or you know, they want to rewatch something. I know they're not interesting. It's a stupid physics lecture. It's not going to be interesting all the time. Sometimes it's interesting to me, but I've listened to this. You see, in my head, I have a voice like a rock star. I know the silky sounds. That's what I hear in my head. But I've listened to my videos. They're mind-numbing. And I have this nasally, whiny sounding voice on them. I've even thought, this is how narcissistic I am. I've actually thought of like remixing them to try and punch up the bass on my voice just a little bit so I can give it kind of that mellow Barry White sound. But again, too much work. I just want to get them out there. There's like hundreds of them out there and all lame. So every once in a while I go and I throw all of them away. I highlight because it's not easy to do in YouTube. I don't know if you know this, but YouTube really doesn't make it easy to like do bulk things to your videos. But hold on. If this is who I think it is, I have to answer them. We have another COVID thing going on. Well, I'm friends with some folks that hold on. Now that we've got a total interruption. All right, back to work. So here we go. Work is a line integral. And what that means is we are taking into account the path that the object travels upon. And that's why it's important. It's not just displacement. The actual path traveled is important for calculating work. And this has to be brought up because what we're about to do is transform the definition of work into our way of dealing with potential energy with charges, which is the whole foundation for energy in a circuit. So we start with this because we need to understand how this is affected by dealing with fields and then how this is affected by dealing with the motion of charged particles. So this integral is a little different because there's actually 3 things involved with this integral, not 2. Now, we don't have to worry about the splitting the integral or anything like that. But, and I say this very clearly, you need to remember that this can also be expressed as dw over dx equals f, because this is where it came from. Which if you're not careful, you'll miss as an important detail. We won't talk about this as much in mechanics, but in here, it's exceptionally important to see this. You see, the problem that we have in this discussion is that force and displacement are vectors, but work isn't. You will need to be able to go from the electric potential to the field and from the field to the electric potential. In one of those directions, you have the direction of the field to work with, and you can strip that away to get the electric potential. But if you try to go from the electric potential back to the field, well, we've stripped away all direction. You have to figure out how to get the direction from something where the direction has been stripped away. You see, that's this function, dw dx, has stripped away any semblance of direction. Yet we're supposed to be finding the force from this, and force is a vector quantity. We will have to figure out how to get the direction back after stripping it away. And that's what's hard. That's like, you know, trying to find who the data belongs to after you've anonymized the data. We have to be able to find the direction afterwards. So we're going to start with this function and talk a little bit about how this integral is slightly different than what we've talked about before. First, we will very seldom ever do this integral without having definite boundary conditions, a starting position and a final position. Next, when we do this integral, we need to have either a constant force or a force whose function is known with respect to position. In mechanics, this doesn't hardly come up unless we talk about gravity. In E&M, it comes up all the time. In fact, the reason it comes up all the time is because we will seldom deal with force in this class. What we will deal with is the fact that force is actually a function of the electric field, which means when we calculate work in this class, we're going to be calculating work like this. That work is actually QE times the dot product with dx. And then we integrate from one position to the next. Now, keep in mind, we have seen lots of different kinds of electric field functions. I'm bringing these up because although this has x in it here, x is just a placeholder for position. And in this case, displacement. So we have these functions that have position in them all the time. So here, our electric field changes as 1 over the location squared. So we have an electric field that is changing depending on where you are. So if we move a particle through that kind of field, we will need to take into account the function that describes how the field changes as we move the particle through that field. It's easy to start with a function that's a constant, something where the field doesn't change with respect to location. That's easy. That's why we tended to do all this work here in the gravitational field. MGH made it easy because mg was a constant. The weight of an object wasn't changing very much. All we had to do is worry about the height. So if we have a constant electric field, all of this just comes outside the integral once we have dealt with whatever issues we have with direction. But that is not the likely scenario in here. We've spent the last 6 weeks showing how electric fields can be kind of funky and have weird dynamics, which means calculating how much work it takes to move charges is going to have all of those dynamics involved in it, now with us having to take the integral as well. This calculation for finding out work is not always easy, and made doubly so because you guys don't have the necessary experience dealing with integrals yet. But you will. So in summation, I want to say that our calculation for work is about moving a charged particle in an electric field. And I'm going to restate it using slightly different nomenclature. The charged particle doesn't change as it's being moved, so it can come outside the integral. When we talk about work, we are integrating the electric field across some change in position from one location to another location, generally taking into account how the direction of the field changes or is maintained with respect to where we are in the field. Now, that gives us the energy. But like I tried to talk to you guys about the beginning of this whole conversation, way back when we were talking about being on these slides, electronics is far less about how much energy there is and a lot more about what you can do with that energy. That's why a battery doesn't tell you how many joules of energy there is, but a battery tells you how many volts it has available. Because for us, it's a lot less about the energy and a lot more about what you can do with that energy, which is how we define the electric potential. The electric potential is defined as the work per unit charge. This is the electric potential. It's defined as the work per unit charge and is based on the physical quantity of work, but based on it in such a way that we divide out the amount of charge that we used to find that work. So if you remember back to finding the electric field, we said we put a test charge out there someplace in space, and we wanted to see what the force was on the test charge, and then we divided away the test charge. And that gave us the electric field. If you remember, the electric field was defined as force divided by charge. The electric potential is defined the same way. How much work would it take to move charges, and then divide out by the amount of charge? And that gives us the electric potential. Its units are joules per Coulomb, which has been given the name volt after Alexander Volta. Now, let me just pause for just a minute and let me tell you, why do we keep doing this? Why do we keep having these measurements that don't have anything to do with charge, when it seems like the whole point of electronics is about moving charges? But every single function seems to take away the charge almost immediately. Here's Coulomb's law, now take away the charge. Here's doing work, but we want to do it without the charge. The reason? We didn't know it was charges when this stuff was being developed. We didn't know what charges were. They didn't know there were charges. Current and voltage were discovered and manipulated before they knew it was the flow of charged particles. Coulomb comes about 70 years later. Alexander Volta found a way to weld using a process that had something to do with batteries. He was creating the first welding system to try and arc weld a system together without having to use some kind of solder. His goal was to develop a process that would make stronger welds in order to make better war machines. So he was developing a system, and he didn't know it at the time, but that system would eventually be a sustainable battery. But at the time, he was trying to arc weld using something that looked like lightning. He didn't know what he was doing. He didn't know what he was manipulating. Louis Ampère was doing something similar, trying to find a better way to manipulate energy to deal with, in the same kind of way, arc welding. So although we have these definitions now that deal with charge, it was all derived before we knew there was charge, that there was charged particles or what charges were. So the battery and the flow of current are actually the base units of electronics, volt and amps. They are later determined to be based on charge. But at the time, an amp was not defined based on charge, and neither was a volt. They became based on that later. So when we look at all this, it was all done backwards, which is why a lot of these feel like they're backwards. As we discovered more and more about what was actually happening, we had to go back to this kind of work and realize, wow, well, we defined it one way, but it really meant something else, which is why a lot of it feels the way it does. So let's talk about how we're going to use this, and let's deal with a simple idea. The rest of this for the next couple minutes will just be, yeah.
Could I ask a question? Sorry.
Of course, Joe.
So like before you were describing how like either like a professor believes in electric fields or electric potentials, but like the electric potential is based on the calculation of the electric field. So like how does that like reconcile with each other if it's like one is based on the other instead of like believing in one over the other?
Interesting question. I'm going to attempt to answer it. I'm going to attempt to, okay? So give me just a second to come up with an attempted explanation. Okay, here's my attempt at an explanation. It's not going to be very good, but it's my attempt, okay? And everybody in the room, I think this is a pertinent question because we're going to do this in a couple of days. Have you ever seen a topography map? So a topography map will look something like this. Does that make sense? You guys have seen something like this before, like a topography map. It gives us the contours of the geography. So it could be that this is every line is spaced every 20 feet of elevation. When we're looking down on it, we are seeing that there's appears to be a hill or a valley, depending on whether these are going up in elevation or down in elevation. So if it was a true topography map, there'd be a key that would indicate whether we're increasing in our height or decreasing in our height. So let's say for a moment that these lines are spaced every 100 feet of elevation. So this being 0, so sea level, and this is 100, 200, 300 above sea level. Well, what does this look like from the side? If I wanted to know what the contours were, could you figure out what it would look like? Like, could you figure out how you could move and not change your potential energy? And could you figure out how you could move and change your potential energy? Like, if I were to move this way along this line, my potential energy would never change because my elevation is never changing. But if I decided to move this way, then I would definitely be changing my elevation, so my potential energy would change. Does that make sense so far? It takes no work to travel along one of these lines. It takes work to go from one line to the next. We follow along with that? So what if these lines, instead of being elevation, represented voltage? So 0 volts here, and I could say 100, let's not deal, let's say 10 volts, 20 volts, 30 volts. Increasing voltage as I go towards the center here. it would be, is it obvious or unobvious that there might be a concentration of charge at the top inside that small circle? It's hard to get there because I'm working, it takes energy to get up there. I'm climbing a mountain to get there because the 30 volts at the top, it requires energy to get to that 30 volts. It'd be likely that inside there's a positive Q that has some kind of charge distribution and is creating an electric field around it. I'm having to climb elevation to get closer. Are we following this discussion kind of? People who believe that the potentials are what's happening in the universe believe that these elevation levels are real things, that the elevations exist. And because the elevations exist, that they're what dictate the direction of the electric fields. I mean, if this goes back to being a hillside and you were to drop a ball here at the very top, could you figure out how it would roll down the hill? Well, yeah, you probably could. So what's real? The field that pulls the ball down, or the fact that it's a hill and it's inclined? The effectiveness of whether potentials are what really are happening in the universe or fields are happening in the universe is not as clear cut and obvious. Is it the potential that creates the field, the change in energy? Or is it the field that creates the energy? Potentials are about energy. A lot of physicists believe that energy is primal and exists kind of apart within the universe, and that fields are a reaction to the energy that's there. But some physicists believe that the fields are there first, and that energy exists only in working against those fields. It's chicken and the egg, if you ask me. So when you ask, well, which one do physicists, why would a physicist believe one versus the other? I can't tell you that, because I'm not sure how a physicist goes about trying to prove which one of these is more fundamental than the other. Is there energy without there being a field? No, there can't be. Well, maybe, right? You can have kinetic energy. Kinetic energy exists apart from any fields, it's just motion. So people who believe in potentials believe that energy is a more fundamental concept, and therefore, because energy can exist apart from fields, then the potential must be the more foundational part of physics. Does that make sense? That's the best explanation I could come up with on the spot. So it'll have to do, because I'm pretty sure that was the bell.
Yeah, that was helpful. Thank you.
All right, guys, have a good day. It was nice to see you all today.